What's up, everyone? Today we're going to do a cool problem where we're going to try and find the shortest path between two nodes in an acyclic graph. So let's look at this. Let's go ahead and look at this example that we have here. And it's maybe a little hard to see, but basically these nodes, 1 points to 2, 2 points to 5, 5 points to 4, 4 points to 1, and both 1 and 4 point to 3. So in this example that we have, we want to find the shortest path from 2 to 3, and it's pretty easy to see that goes from 2 to 5 to 4, and then 4 points directly to 3. And there's also, if we were looking for any path, another valid path would be 4 to 1 to 3, but we're looking for the shortest path, and so skipping the 1 and going straight from 4 to 3 is the way that we want to do this. So let's go ahead and dive right into this problem, and the first thing we want to do is make sure that we clarify the problem and understand exactly what we're being asked. So for example, one thing that we might want to check here is this an acyclic graph or not? They haven't specifically told us anything in the question one way or another, so we definitely want to check and we don't want to assume one way or the other. In this case, I'm going to solve this problem as a potentially cyclic graph. So I'm not going to assume anything about whether or not there are cycles in the graph, but this solution would work if it was an acyclic graph. It's just we're going to have to do a little bit of extra effort to make sure that we don't end up in any weird cycles or anything like that. And this would also be, we're basically going to do the same solution as we would do if we were to look at an acyclic graph, or sorry, an undirected graph, because an undirected graph is going to be much more likely to be a cyclical graph because we're going both directions. So we want to clarify that. We also want to double check, what are the types of the nodes? Or what is the type of data stored in the node? In this case, it honestly doesn't really matter because we don't really care what values are in the nodes. I've obviously represented them as integers, but I can actually we're going to implement the code without even worrying about that. We also might want to think about, what are we going to do if there's no path from the one node to the other in the graph? So in this case, I'm going to return a null. I'm going to return a list, and I'm going to return a null list if there is no path, and otherwise I'm going to return a list with some number of elements in it, because even if the one node points directly to the other node, that still gives us a path of length 2, right? Because we have the start node and the end node. And as you can see here, we included both the 2 and the 3 actually in our list. So that will be good, and let's now think about how we're actually going to solve this problem. So hopefully, as soon as you see shortest path, what should jump out at you is breadth first search. Because by doing breadth first search, we're going to start with a single node, and then we're going to look at all the nodes that are 1 node away from it. And then we're going to look at all the nodes that are 2 nodes away from it, and so on and so forth, incrementally moving outwards. And so we can stop our algorithm as soon as we find our destination node, or the node that we're looking for. We don't have to go through the entire graph to find every possible path from one node to the other, because potentially if we had a big graph, we could have to do a huge amount of work. And the runtime is actually going to be the same whether we do depth first search or breadth first search, but in this case, just because we are optimizing it slightly, the average time is likely going to be better in most cases if we do a breadth first search instead of a depth first search. So we're going to do a breadth first search, and the only complication here is that we're going to have to actually keep track of what our path is from one node to the other, because we don't just want to find whether or not there's a path, but we actually want to find what that path is. And so let's go ahead and actually start writing the code, and we can talk about this as we start going. But first we're going to have to implement a node class. So a private inner class called node, and that I'm going to represent. It could have a value in it. I'm not going to bother because that's not necessary. And what it is going to have is a list of nodes that is going to represent all of the child nodes, or all the nodes that it points to. So lists node next, and that's going to be our entire node. And then we're going to implement our actual shortest path method, which is going to return a list of nodes as well. So I'm going to call that public list node shortest path. And that's also going to take in 2 nodes, right? I'm going to take in a node A and a node B. So now let's think about what we need to do. So for breadth first search, hopefully you remember what we're going to do is create a while loop, and we're going to add each round in the while loop, we're going to create a queue. And that queue is going to contain all of the nodes that we have yet to visit. And so we're going to start by adding our initial A node to the while loop. And then we're going to loop through the while loop, grab that off the queue, and then add all of the children of A to the queue. And we're going to continue to do this by pulling the front item off the queue and adding all the children to the queue. But then we also want to track the actual path that we're taking, and what we can do for that is we can actually just keep track of what is the parent of each node. So let's imagine that we get to this node 3, and so what we're going to do is basically retrace our steps. So we know when we're going through the algorithm that the parent of 3 was 4, and so we can create a hash map that maps the node to its parent. So we'll map 3 to 4, 4 to 5, 5 to 2, and 2 is the beginning of our list. So 2 can be mapped to null. The parent of 2 can be null. And so, because we're not actually looking at every parent, we're only looking at the parents that we've traversed through our tree. So we're going to add those parents, and then we can start with our final node and just reconstruct our list. So we can get the parent of 3 from the hash map, and that'll be 4, and then get the parent of 4, and then the parent of 5, and then the parent of 2 is null, and so we know that we're back at the beginning of our list, and we can just reconstruct the list like that. So hopefully this will make more sense as we're actually putting it into code, but that's basically what I'm going to do. And that also, the other thing that we need to do is we need to make sure that we don't visit a node more than once, because since we could potentially have a cycle in our graph, like we have this cycle going around like the 4 corners of this square, we could potentially end up with some problem where we would do a search from where, let's say we were looking for 3. We would go, and we were starting at 1. We would go from 1 to 2, 2 to 5, 5 to 4, and 4 back to 1, and then that would be problematic because we could end up continuing and searching around this square forever. So what we're going to do is, and that would also be hard because then potentially you could have more than one parent of the same node. And we can't map, so we can't easily then reconstruct our path backwards, because we're going to, let's say we took the path we went from 4 to 3, and then we were at 1, and we went from 1 to 3, then when we're going backwards, are we going to 1 or are we going to 3? And so what we're going to do is we're going to use that same hash set, and we're going to check before we add a new node to our list whether or not we've already visited that node. So hopefully this will make sense as we write the code. First thing, obviously, we just want to check and make sure that our input is valid. So if A equals null or B equals null, we're just going to return null. B equals null. So, and then we're going to have to create our queue and our hash map. So I'm going to create a queue of nodes, and I'm going to call it toVisit because that's going to be the nodes that we haven't yet visited, but that we have seen in our tree, and that we have to visit on our next pass through or whatever. So that's going to be a new linked list of nodes, and then I'm also going to create a hash map that's going to be the parents. So this is going to be mapping from one node to another node, and I'm going to call it just parents, and new hash map node, just like that. So far so good. We've basically just created what we need, and so to initialize this, we want to add A to our hash map and A to toVisit. So we're going to say toVisit.add A, and parents.add A. And so, and actually, we have to do at A and null, right? Because as we said, the parent of A is going to be null, and that way, when we're going backwards through our list, we will be able to just see that the parent of A is null and know that we've gotten to our starting point. So now we're going to implement our while loop, and we want to just say while toVisit is not empty, because we're just going to keep going as long as we continue to have nodes. If we haven't found our node that we're looking for, our B node, then we want to just keep going. And we're going to break out of this if we find B. But if we don't find B, we want to keep going. So we'll do this while loop until it's empty. And we start by removing a node from the queue. So node cur is equal to toVisit.remove. And we first want to check if that's equal to B, right? Because if that one's equal to B, then we've found our full path to B, and then we can break out and reconstruct the path. So if cur equals B, then we're going to break. And otherwise, we want to add all of the children of cur to our queue. And then we also want to add their parents, or we want to add the parent to our hash map. So we're going to say for node n in cur, we are going to just add them. So we're going to say toVisit.add n, and we're going to say parents.put n and cur, right? Because we know, since we're at cur now, that cur is the parent of n. And so by doing that, we're going to be able to go traverse backwards. And then if we're going to just keep doing this until we get to the end, and then we can start down here. So we've now constructed our entire hash map. So we're in one of two things has happened. Either we found our B node and we broke out, or we reached the end and we ran out of nodes. We basically traversed every node that we could from A, but haven't found B. And so we want to first obviously check, because if we haven't found B, then we should be returning null, right? Because there is no path to B. And we can check if we found B by just checking for B in parents. So if parents.getB is equal to null, then we return null, right? Because if parents.getB is equal to null, that means that we never added B to parents. And so we are going to, right, so we never reached B in here and we never added it. So our result should be null. So we return null. And otherwise, we're going to traverse our list. We're going to traverse our hash set, basically. We're going to traverse this weird linked list sort of thing that we've constructed and recreate our list. So I'm going to create a list that is going to store my result, first of all. So I'm going to just create list node, and I'm going to call it out, because it's our output. Is going to be a new linked list of nodes. And then I'm going to say that node, I'm going to create some temporary node that is going to be the one that I'm going to traverse through. So I'm going to say node cur equals B. And then because I'm traversing backwards from B, right? Because it's easy for me to find the parents of B versus if I started from the other direction. If I started from A and tried to traverse down from A to B, there may be multiple paths I could take, but there's only one path going backwards from B to A. So that way I know I basically have the path, versus if I were going the other direction, I'd have to figure out which way to take. So I'm going to say while cur is not null, I'm going to, and what I'm going to do here is I'm going to add my node to the beginning of this list. And I want to add it to the beginning of the list because I want to make sure that this is in proper order from A to B. And so since I'm starting at B, I need to basically reverse the list, which I can easily do by adding each item at the beginning of the list. So what I'm going to do is say out.add, and it's 0 cur. Because you can either just add cur, which adds cur to the end of the list, or you can specify an index and then cur. So I'm specifying index 0, so I'm adding it to the beginning, and then I'm saying that cur is going to be equal to parents.get of cur. And finally, return out. And so hopefully you can see here I'm starting with B, and then I'm adding B to my list, and then I'm saying that B equals cur, and then I'm adding cur to my list, and then traversing like one back in this list that I'm creating, right? I'm saying cur is equal to the parent of cur, and I keep getting the parents until I eventually get back to my original node. So hopefully that makes sense. That's our whole code for this problem, and let's just test a very simple example. So we can, let's look at this graph that we have here, and we can maybe do something a little simpler than a little shorter. We can go from, let's say, from 5 to 3. So we're going to check that 5 and 3, so we have shortest path 5, 3. And then we're going to start by checking that they're both neither null, and they're not. And then we're going to say that toVisit is going to be equal to an empty queue, and parents is an empty hash set. And then we initialize them by saying we add 5 to toVisit, and we add 5 null to parents. So then we're going to say while toVisit is not empty, we're going to cur equals toVisit.remove, so cur equals 5, and then we're removing that from toVisit, and then 5 has one child, which is 4. So we're going to say toVisit.add 4, and then parents.put 4 and 5. For 4 mapped to 5. So we're going to get this. Then we loop again. That was the only child, so we come back and we remove this node 4. And 4 is not equal to 3, which is what we're looking for. So we come to this for loop and we add both children. So we add the 3 child, which is going to be here. Or let's do this, make it slightly more interesting. First we add 1, and then we add this mapping of 1, 4 to our list, and then we're also going to add 3. And so we add this mapping 1, 3 to the list. We add 3, 4 to the list. So now we're going to loop through again. We remove the 1, and then we're going to see that, so we come down here and we remove the 1. 1 is not equal to our current node, and then we're going to add the children. So we're going to add 2 to our toVisit, and we add the mapping here, so 2 maps to 1. And then we actually are going to try and add 1, we're going to try and add 3, and that's a problem, right? Because we shouldn't, what we're running into an issue here is because we have not actually checked whether our list is, or whether our graph is cyclical or not. And so what we actually want to do is we want to check that we haven't visited the node first before we try and add it to our list, because we don't want to keep visiting it again and again. And so what we should actually do is we can check this by checking whether we have our node mapped to in parents or not, right? Because what we're trying to do is we're trying to add 3, but 3 is already in here. We already have a parent for 3. And so we can just fix this slightly by adding an if parents dot contains key n, then that's going to be the only case in which we're actually going to want to add our node, right? Because we're not going to add the node if it already exists in the list. And so like this. So what we're going to do now is we're going to skip this last one. So we're not going to add 3 again. And then we're going to loop through one more time. We're going to remove 3. And then we're going to see that 3 is equal to B. And so we're going to break out. And now, let's come down here. So this is now, we're not going to need to visit anymore. And I'm just going to move this down lower so that we can see better. So we have this parents map here, and we are going to say if parents.get b equals null, and b is 3, right? So as I could, let me copy this too. So b is equal to 3, and that's not null, or parents.get 3 is not equal to null. So we're going to create a new list. So we create out, and that's going to be this empty list. And then we're going to say that cur equals b, so cur equals 3. And then we're going to add that to the list. So we add 3 to the list, to the beginning of the list, which is the only position that we have. And then we say cur equals parents.get cur. So 3.get cur, or parents.get 3 is equal to 4. And then we're going to loop again, and we're going to add 4 to the list, and we add it to the beginning. And then we get 4, and 4 maps to 5. So 5. And then we add 5. And then finally, 5 maps to null. So cur is now equal to null, and then we return this out list. And as you can see, the shortest path from 5 to 3 is in fact 5, 4, 3. So that's all there is to this problem. Hopefully that made sense. It's a little bit tricky, especially the tricky part with this problem is actually retaining the path that we took, right? The actual breadth first search, hopefully that should be fairly intuitive or easy at this point. From just doing these problems, it gets really easy, but tracking the actual nodes that you were following is a little more tricky. So it's really good to know how to do that. Just very briefly, runtime for this. Since we could potentially visit every node once, the runtime for this is going to be big O of n time. And we're not going to visit the nodes more than once because of this thing that we missed earlier on, but we fixed. And then in terms of space, it's also going to be big O of n, because potentially you could imagine a tree or a graph where there's one node that points to every single other node. And so you would start, and if you start at that node, you would add every other node to your queue, and that's the space that you're taking up. So that would be your largest possible space, would be big O of n. And so that's all there is to this problem. Hopefully that made sense. Let me know in the comments below or on the blog if you have any questions. And otherwise, I'll see you guys again next week.